All right. So remember that the net work done by a cycle is just the area inside of the cycle. If it's a clockwise cycle, it's positive work. If it's anti-clockwise, it's negative work. Now, this is why it's positive work. Is that notice that the only parts of this, the processes that do work are BC and AD, right? This is positive work because the piston is moving out. Notice it does positive work at a higher pressure, so therefore it's going to be more work. And it does negative work, or work is done on the gas at a lower pressure. Okay? So our area is the work, is the height times the width. Right? So the height of this is 400 pascals, from 200 to 600. And then the change in volume here is 2 cubic meters. So that is 800 joules of net amount of work, right? Now you could do it, the other way to do it, right, is to say, well, let's see, the work done by this is 600 times 2, that's 1,200, and then the work done on it is negative 400, and 1,200 plus negative 400 is 800, okay? But, I like the area method myself, okay? And then it says, what is how many moles do you have? Well, moles are, from the ideal gas law, PV over RT. And so our pressure at A is, what is it? It's 200. Our volume is 1. R is still 8.31. And then they tell us that it's 60 kelvins, right? So let's do that. Let's see, 200 times 1, don't forget to multiply by 1, divided by 8.31, divided by 60 is 0.401123. Okay, how many moles? And what are the temperatures at the other vertices? Now, you could just, now that we know the moles, you could just bust through this and say, okay, temperature is PV over NR, right? And you can read the pressure and volume off of this thing, right? That is one way to do it, okay? But let me encourage you to possibly do it a different way, right? Because notice that these numbers are kind of even-looking numbers, aren't they? Okay, so the other way to do it is if this is 60 kelvins, right? Well, here we just increased the pressure by a factor of 3 from 200 to 600. So is it possible that the temperature went up by a factor of 3? Yes. Right? Okay, so the temperature at B is just going to be 3 times the temperature at A, right? So 3 times 60 is 180. Okay? Now if you don't believe me, go ahead and just do the maths here. Okay. And then notice here that we then multiplied the pressure by a factor of 3. We went from 1 to 3. So the temperature at C is going to be 3 times the temperature at B. So it's going to be 3 times 180. And 3 times 180, this is higher maths, that's 540 kelvins. So this is the highest temperature, right? That's 540, this guy's 180. And then D here, let's see, D, okay. So D is we cut the pressure by a factor of 3, right? So temperature of D is going to be 1/3 the temperature at C. So it's 1/3 of 540. Is 180 again. Kind of a weird thing, right? Okay. The other thing you could do is you could say, look, if I went this way, from A to D, I would multiply the temperature by 3. That's the other way to get that, right? Okay. So there you go. The other vertices. I think on the tests, there's not going to be, it's going to be some uneven number, right? You might feel more comfortable using the ideal gas law. Let's just for kicks, let's find the temperature at C doing that, right? Temperature at C. Pressure is 600. I'm just reading the graph here. The volume is 3 divided by n is 0.401123. R is still 8.31. So let's try that. 600 times 3 divided by the number, I'm just going to use the number from my calculator, it's not rounded, divided by 8.31. And it, oh wow, it comes out even to 540. It's up to you. You know, I encourage you to use just proportions and stuff, but you know, it might not be simple that way. I don't know. All right.